There's a place in the universe where time doesn't slow down, doesn't speed up. It just stops being a direction you can move through at all. Even light can't find a way out. Scientists call it the event horizon, and for decades, it sat there in Einstein's equations like a warning sign nobody could read. Then, in 2015, we felt one of these things shaking the fabric of reality. A ripple so faint by the time it reached Earth, after traveling over 1 billion light years, that it moved our detectors by less than the width of a single atomic nucleus. And that signal changed what we thought we knew. Imagine you're falling towards something, and the closer you get, the slower your watch ticks. Not because anything is wrong with the watch, but because time itself is running thinner. And at some point, right at the edge, it stops being something you can move through at all. Black holes aren't just really heavy things in space. They're places where space-time gets bent so hard that the geometry of the universe breaks down in a way that's genuinely hard to get your head around, even for the people who study them full-time. And the part most explanations skip over is actually the strangest part. To get a feel for how massive objects bend space-time, think about how a star or a planet shapes the path of everything around it into an orbit, pulling things into a curve the way a slope pulls a rolling ball. Black holes do that to an extreme that stops making intuitive sense. Inside the event horizon, space and time swap roles. The direction toward the center stops being a place and becomes a moment in time, one you're falling toward the same way you fall toward tomorrow. You can't choose not to fall inward any more than you can choose not to age, because inside a black hole, the future only points one way, and that way is down. From the outside, if you watched someone fall in, you'd never actually see them cross the horizon. Their image would freeze and redden and fade, stretched across the edge, because the light coming off them is fighting harder and harder to climb out of the gravity well and losing that fight a little more with every meter. What actually happens at the event horizon isn't a physical wall or surface, and it definitely isn't an explosion. It's a boundary where the question, what comes next, stops having a spatial answer and becomes purely a question about time, one that only runs in a direction you can't reverse. The person falling in doesn't feel a moment of crossing. They just fall. The horizon passes them without any ceremony, and then the geometry around them quietly becomes something with no exit. From the outside, you see them freeze. From the inside, they keep falling. Both are true at the same time, and that's not a trick of language. It's just what general relativity actually predicts when you follow the math all the way to the end. So physicists sat with this object in their equations for decades and argued about whether it was real or just a sign that the theory was breaking down. Then a different question started nagging at people. If two of these things ever collided, what would that do to the space around them? For most of the 20th century, the working assumption was pretty simple. Gravitational waves, if they existed at all, would be so tiny that no instrument humans could ever build would pick them up. Einstein himself doubted they could be detected, and some physicists weren't even convinced they carried energy at all. A gravitational wave is a ripple moving through space-time itself. Not through space the way a wave moves through water, but through the actual fabric that space and time are made of. When two massive objects spiral toward each other, they squeeze and stretch space-time as they go, sending those ripples outward at the speed of light. By the time those ripples reach Earth from any realistic source, the stretching they cause is smaller than 1,000th the width of a proton. LIGO solved this by bouncing laser light back and forth along two perpendicular arms, millions of times over, so that even a stretch that tiny shows up as a shift in how the light waves line up when they meet back in the middle, getting the noise floor low enough that a real signal could survive. Above it took decades of engineering. On September 14th, 2015, at 5:51 in the morning Eastern Time, both LIGO detectors registered a signal, It lasted less than a second, swept upward in frequency, and then stopped. When scientists converted it into sound, it came out as a brief rising chirp, produced by two black holes each around 30 times the mass of the Sun spiraling together for billions of years before merging over a billion light years away. The energy released in that fraction of a second exceeded the combined light output of every star in the observable universe. They trusted it because the signal arrived at the Louisiana detector first, then the Washington State detector 7 milliseconds later, exactly consistent with a wave traveling at the speed of light from a specific point in the sky. Spacetime isn't just a concept or a coordinate system. It's a physical thing that shakes, and you can build something sensitive enough to feel it. Since then, LIGO and its partner detectors have picked up dozens more events, including black holes merging that are far too heavy to have formed from any dying star we know of. One event involved two black holes each around 130 times the mass of the Sun, which suggests they weren't born from collapsing stars at all, but from older black holes that had already merged once before. Something about how black holes form is still wrong in our models, and the detections keep making that harder to ignore. And the more we look, the stranger these objects get. Something should bother you about black holes. They swallow everything. Nothing gets out. Not light, not matter, not anything. And yet some of them are shooting jets of plasma thousands of light years long, moving at around half the speed of light, out into the galaxy around them. Where is that energy coming from? The jets don't come from inside the event horizon. They come from just outside it, where matter piles up into a spinning disk, gets compressed and heated to billions of degrees, and starts interacting with a magnetic field threaded through the whole system. The black hole itself is spinning, and when spacetime spins, it drags everything nearby along with it, including those magnetic field lines, and that dragging flings material out along the poles. The energy comes from the rotation of spacetime itself, not from anything that crossed the horizon. Some black holes do this in bursts. One type can sit dormant for 100 million years, then wake up and blast out plasma so violently it carves structures a million light years wide, like a cosmic volcano going off after geological silence. Researchers have now traced the actual base of one of these jets, M87, to a region about 0.09 light years from the black hole itself. A collaboration of radio telescopes linked across the entire planet, effectively building one Earth-sized dish, produced the first direct image of a black hole's shadow. It showed a dark center surrounded by a bright ring, and that ring isn't just light traveling straight toward us. It's light that looped around the black hole multiple times before escaping. One side of the ring glows noticeably brighter than the other, because the matter spinning toward us gets boosted by its own velocity, and the side spinning away gets dimmed. That brightness difference is at the heart of what general relativity predicts for a spinning black hole with an accretion disk around it. It's a photograph of curved spacetime. But every piece of matter that falls past the horizon carries information. What it's made of, what state it's in, all of its quantum properties. Quantum mechanics says information can never be destroyed. It can be scrambled and hidden, but it can't just disappear. General relativity says everything past the horizon is causally cut off from the universe forever. Both theories have passed every test we've ever thrown at them, and they're flatly saying opposite things about the same situation. Stephen Hawking spent decades on this problem and changed his answer more than once. The current best idea involves black holes slowly leaking energy over astronomical timescales. But whether that leaking carries the lost information back out in any recoverable form is still genuinely unresolved. And that unresolved tension isn't just a problem for black holes. It runs straight through the foundations of how we think physics works. General relativity and quantum mechanics are the two most tested theories in the history of science, and every experiment we've ever run has confirmed both of them. When you try to apply them to the same situation at the same time, though, the math falls apart and spits out infinities that don't mean anything. Relativity treats space-time as smooth and continuous, curved by mass and energy, like a stretched sheet bending under weight. Quantum mechanics says everything at the smallest scales is chunky, probabilistic, and governed by uncertainty. When you try to apply quantum rules to space-time itself, the equations produce infinities that can't be cleaned up the way they can in every other area of quantum physics. The place where this breaks down hardest is the center of a black hole, where density goes infinite, curvature goes infinite, and general relativity stops producing numbers that mean anything. Quantum mechanics should take over at that scale, but we don't have a version of quantum mechanics that includes gravity, so there's nothing to hand off to. Physicists have been working on this for almost a century. String theory proposes that particles aren't tiny points, but tiny vibrating strings. And in some versions of the math, gravity falls out naturally alongside all the other forces. Recent work using a technique called bootstrapping, starting from basic principles and seeing what the math forces you toward, has shown that under certain strict assumptions, string theory might be the only mathematically consistent way to describe some kinds of particle interactions. Those assumptions require flat spacetime and maximum symmetry, conditions that may not describe the actual universe. So string theory stays a candidate rather than a confirmed answer. Other approaches try to make spacetime itself chunky and quantized, and some newer ideas suggest that spacetime, and even time itself, might not be fundamental at all, but built up from quantum entanglement between smaller pieces of something we don't have a name for yet. There are now real experiments being designed to test whether gravity is quantum. One involves cooling tiny silica particles around 150 nanometers wide to their lowest possible energy state and letting them interact only through gravity. If they become entangled through that interaction, gravity is quantum. A separate proposal from researchers at University College London wants to weigh a dense 1 kilogram mass with extreme precision to see if its weight fluctuates slightly over time. Because if it does, that would mean space-time behaves classically rather than quantum mechanically. These experiments haven't been run yet, and the engineering is brutally hard, but they're real proposals with specific things they'd falsify. And the theory that predicted black holes, gravitational waves, and the bending of light around stars has now survived over a century of tests without breaking once, which makes the one place it does break down all the more worth understanding. Einstein wrote those equations knowing they contained something he couldn't explain away. The theory is powerful enough to predict two black holes merging over 1 billion light years away, and it's passed every test you can throw at it. But right inside its own math sits the place where it breaks down, and that's not a flaw someone missed. Einstein saw it and wrote it down anyway. The next step isn't just finding a new equation. It's figuring out what reality actually is at the level where space and time stop being the foundation. The theory sees across the universe. It goes blind the moment it looks at its own center.